In this video, we're going to wrap up section 6-7, and this is also the end of chapter 6. And our last topic is harmonic motion. The periodic nature of trigonometric functions is useful to describe the motion of a point of an object that vibrates, oscillates, rotates, or is moved by a wave motion. For example, consider a ball that is bobbing up and down on the end of a spring, as shown in the figure down here. Suppose that 10 centimeters is the maximum distance the ball moves vertically upward or downward from its equilibrium, or its at-rest position. So here we are at equilibrium, the ball's hanging there, the spring is extended, and we're at the 0 point, sort of like a baseline. When the string is fully stretched out, we're down here at -10, and when the spring is pushed all the way up and compacted, we are at +10. Suppose further that the time it takes for the ball to move from its maximum displacement above 0 to the maximum displacement below 0 and back again is 4 seconds. So let's say we're here up at where the spring is fully compressed. To have the spring fully extend and then come back up takes 4 seconds. Assuming the ideal conditions of perfect elasticity and no friction or air resistance, the ball would continue to move up and down in a uniform and regular manner. So from this spring, can you conclude that the period, or from the spring you can conclude that the period, the time for one complete cycle is 4 seconds. That's our period. Its amplitude, its maximum displacement from equilibrium, is 10 centimeters. Again, that's from our equilibrium. We go up 10 or we go down 10. Its frequency, the number of cycles per second, is 1/4. Motion of this nature can be described by a sine or a cosine function, and it's called simple harmonic motion. So here's our definition. A point that moves on a coordinate line is said to be in a simple harmonic motion if its distance d from the origin at time t is given by either a sine or a cosine wave. So a point that moves on a coordinate line is said to be in simple harmonic motion if its distance d from the origin at time t is either given by distance equals a times sine of, that's little Greek letter there is omega, the sine of omega times t, or d equals a times the cosine of omega times t, where a and omega are real numbers and omega is positive. The motion has amplitude a, absolute value of a. The period, remember when we found the period of sine and cosine, it was always 2 pi divided by what was in front of the variable. Well, here it's omega. And the frequency is, just turn it upside down. If we flip the period over, we get the frequency. So the period is 2 pi divided by omega. Here it's omega divided by 2 pi, gives us the frequency. So in example 6, it says write the equation for the simple harmonic motion of the ball described in figure 6.8.4. That's the ball on the spring, where the period is 4 seconds. What is the frequency of this harmonic motion? So because the spring is at equilibrium when d is equal to 0 and t is equal to 0, we're going to use the sine wave. And let's start piecing some stuff together, what we can figure out here. Well, we know the amplitude is the absolute value of a, and from the picture we know that's how far above and below equilibrium we go, so the absolute value of that would be just 10. The period, we know from where is that? Oop, I moved it up. The period is 2 pi divided by omega. So the period is 2 pi divided by omega, and we know here in the given information the period is 4 seconds. So if we set this equal to 4 and we solve for omega, you know, we multiply both sides by omega. 2 pi equals 4 omega. Divide both sides by 2, we'll get pi equals 2 times omega. And then to get omega alone, we divide by 2. So omega is equal to 1/2 pi. And they were asking us to find frequency. Remember, frequency is where we turn the period upside down. So the frequency is omega over 2 pi. Well, we just found here omega is a half pi. So we're going to have a half pi divided by 2 pi. And you know, a fraction divided by a fraction, we invert and multiply. So I'm going to bring this divisor up and flip it over. 1 over 2 pi, and I'll multiply. And we can see that the pi's will cancel. So we're going to have a numerator of 1, our denominator of 4. Our frequency is 1/4 cycles per second. Cycles per second. And they did ask us, I believe, to write the equation. Write the equation for the simple harmonic motion of the ball described. So we just got to plug in some of the stuff we found. D equals, well, we found the A, the amplitude is 10. We are using the sine wave. We found omega was a half pi times the variable t. So we could plug in any time we wanted for t, any given second or fraction of a second, compute this, and this will tell us our distance from equilibrium. If we get a negative answer, it means we're going down. Negative numbers. If we get a positive answer, it means we're on the way back up, above our equilibrium. One illustration of the relationship between sine waves and harmonic motion can be seen in the wave motion resulting when a stone is dropped into a calm pool of water. The waves move outward in roughly the shape of a sine or cosine wave, as shown in figure 685. So the pebble hits the water and we have that ripple motion. As an example, suppose you're fishing and your bobber is attached so that it does not move side to side horizontally. As the waves move outward from the dropped stone, your fishing bobber will move up and down in harmonic motion. You know, if, let's say here, say here's the bobber. As the waves come out from where the pebble was dropped in, you know, the bobber is going to ride the waves. The bobber will follow a simple harmonic motion. Here in example 7. Simple harmonic motion. Given the equation for simple harmonic motion of distance equals 6 cos of 3/4 pi times t, they're asking us to find a few things here. Find A, maximum displacement. Well, max displacement is just sort of another way to say amplitude. Max displacement is the same thing as amplitude, how far above or below equilibrium is. And for here it's 6. That was easy enough. Part B, find the frequency. Frequency is omega divided by 2 pi. And here omega, you know, that's just what's in front of the t variable. So here's our given omega, 3/4 pi. So 3/4 pi is omega, and we're dividing that by 2 pi. Or I like to do that as 2 pi over 1, because now we have a fraction divided by a fraction. Our numerator is 3/4 pi, and now we're going to multiply by the reciprocal of that, 1 over 2 pi. And we can see on the diagonal the pi's cancel. Multiply straight across the top, we get 3. 4 times 2 is 8. So that's 3/8, you know, cycles per second, or they didn't give us any time unit for this, so cycles per unit of time, or time unit. Part C, find the value of D when t is equal to 4. So we want to solve for D when we plug in a 4 for that t. D equals 6 cos of 3/4 pi times t is equal to 4. So we're going to do 6 times the cosine. 3/4 pi times 4, well, 3 times 4 is 12. 12 pi divided by 4. 12 divided by 4 is 3 pi. Now if we think back to the unit circle, 3 pi. 2 pi is a lap around. 3 pi would be another half circle. What is the cosine value at this point? Well, the cosine value is our x-coordinate. So that would be negative 1. The cos of 3 pi is negative 1. Negative 1 times 6 is negative 6. So d equals negative 6. And the last part, d, find the least positive value of t that makes d equal to 0. This is going to take a little thinking. So I'm just going to copy the equation here and let's think about it. D equals 6 cos of 3/4 pi t. We want a value for this variable t that's going to make the whole thing equal to 0. Well, let's think about the cosine function just by itself. The cosine of, let's use theta. When does cosine equal 0? Well, back to the unit circle. Cosine is our x-coordinates. Well, x-coordinates are 0 on the y-axis. And that occurred at pi over 2 or 3 pi over 2. And we're looking for the least positive value. Well, the first time cosine goes to 0 is when we get to half pi. So what we want to do is set this equal to a half pi. 3/4 pi times t is equal to half pi. So I like to get rid of the fractions right off the bat. I'm just going to go through the whole thing, both sides of the equal sign, and I'm going to multiply through by 4. So these 4's are going to cancel, and we're going to have 3 pi times t equals, if I multiply the 4 over here, I'm going to get 4 pi over 2, and 4 divided by 2 is 2, so 2 pi. And we're solving for t. So we're going to divide by 3 pi to isolate the t variable. We're going to also divide this side by 3 pi, and the pi's cancel. So t equals 2/3. When t is equal to 2/3, this whole thing is going to go to 0, because it'll be the cosine of a half pi. The cosine of a half pi is 0. 0 times the 6 that's already there is equal to 0. Okay, there's only one problem for the huddle here, and it's just like that last example. It's a 4-parter. So pause the video, give this problem a shot, turn the video back on, and see how you did. Okay, part A. Here's our function. D equals a half cos of 20 pi times t. Part A is nice and easy. I'll even put it up here. Our maximum displacement is just the amplitude. And in here, that's a half. So max displacement equals a half. Part B. Part B is the frequency. And frequency is omega divided by 2 pi. Remember, omega is just what is in front of the variable. So omega is 20 pi divided by 2 pi. Ooh, this is going to be nice. Pi's cancel. 20 divided by 2 is 10. 10, and that is cycles per second. Or they don't really give us any time units here, so cycles per unit of time, or time unit. Whatever the case may be. Part C. The value of d when t is equal to 5. So we want to know what d is when we put in a 5 for the t. So we have a half cos times 20 pi times, and we're plugging in t is 5. So we're going to have 1/2 the cosine of 100 pi. Back to the unit circle. Here's our unit circle. If we do 1 lap, it's 2 pi. Next lap, 4 pi, 6 pi, 8 pi, 10 pi. Any even multiple of pi is going to take us right back here on the positive x-axis. And what is the cosine value here? Well, the cosine value is still the x-coordinate, so that's going to be a 1. The cosine of any even integer of pi is 1. So we're going to have a half times 1, which is a half. So d is equal to a half when we plug in a 5 for t. And the last part, what is the least positive value of t that will set d equal to 0? Again, just like the last one, cosine of theta. When does cosine equal 0? Cosine is an x-coordinate, and the first place that happens is pi over 2 radians. So we want this to equal pi over 2 radians. 20 pi times t is equal to a half pi. Again, I don't like fractions. Clear them out. I'm going to multiply everything through by 2. So 2 times this term is 40 pi times t equals 2 times this. We'll wipe out the denominator, and we're left with just pi. And to isolate t, we divide by 40 pi. Divide this side by 40 pi, and the pi's cancel. And don't forget, in front of that pi, there was a placeholder. There was a 1 there. So the answer is 1/40. T equals 1/40. The assignment for tonight, there's only 3 problems. 47, 56, 57. Enjoy.